So good morning, one and all. And today we are going to start with something very fundamental to physics, and you will find this application many a times in physics. This is called as Dirac Delta Function. Okay, so Dirac Delta Function is quite ubiquitous in your to physics, and you'll find several applications in scattering theory, or probably in electromagnetic theory or quantum mechanics, everywhere. Like as an impulse of a impulse function also. So you find it quite ubiquitous to physics, especially in quantum mechanics. You'll find certain applications. Then you may find certain applications in electromagnetic theory also. So all these things are uh, all these are the fields where you'll find such applications of Dirac delta function. Now, question arises: what is Dirac delta function? Okay, so let us consider a function. Let us consider first a physical problem and realize uh, as to why it becomes so necessary, or why it becomes so necessary, or why it becomes time and again physics. Okay, so first thing is let us see that if I ask you what is the you can say density of a point charge. So such kind of thing may quite often occur, because see, point charge is very fundamental. You will see that whenever you are writing a Coulomb's expression of force, you talk of something called as point charges. Okay. Now, if someone asks you what is a point charge, what is the volume charge density of a point charge, so you will say, how can I define a density of a point charge whose volume is not defined? Okay. So you'll be at a fix that how can I define density of a point charge, because the density for density you need some volume element, isn't it? So if you need some volume element and you already know that a point charge only resides at a single point. Okay, so a point charge only resides at a single point. Let's say this point is x equal to x naught. So let's say if I'm saying my function my point charge resides at point x equal to x naught, then how will I be able to define the volume density of the this particular point charge? Or probably if there is a point mass and I say what is the volume mass density of this particular point mass, you will be in a fix. You'll be in a fix because you don't have such function which only exists at a single point, and otherwise it does not exist. So it means that if I'm saying there's a point charge on point x equal to x naught, you need a certain definition that your function is only here, and all other points it is zero. Okay, so what do we need in order to define? I'm just giving you an instance example. In order to define the volume charge density of a point charge, volume charge density of a point charge, what does one need? One needs, let's say if I'm saying it is rho as a function of r here, one needs the following definition. And you can see that what is rho? Rho is nothing but it is equal to dq upon dv, right? If I'm saying a point charge, then I mean that my volume element dv is tending to zero. If my volume element is tending to zero, then rho must tend to infinity. It implies what? It implies that the description of a point charge, volume charge density of a point charge, would require a function which is just infinite at a point, and otherwise it is zero. So I would require a function which satisfies this following property, that rho of r should be equals to infinite for r equal to zero, and rho of r should be zero if r is not equal to zero. I hope it is clear. So in general, there is no such well-defined function. So there is no such well-defined function which fulfills our demand. Okay, so there is no well-defined function as such which fulfills our demand, because you see, your function is completely, you have to make a function, because you see, if I write dq upon dv in FSA, if it is a point charge, then obviously it is not even tending to zero, it is exact zero. So it's like 1 over 0 does not exist. I mean, there's no such value there is no such value defined as 1 upon 0. So there is no such well-defined function. Now, for such kind of situations, we need certain different mathematical construct, and one such mathematical construct is called as Dirac Delta function. Okay, so this is called as Dirac Delta function. And why I'm teaching you all this, because see, this you'll find several applications as I go along in quantum mechanics as well as in electromagnetic theory. So we'll take case by case. For example, when I'll be teaching you something in electromagnetic theory, I'll again reiterate you some initial basics, but here I'm dealing Dirac delta function more so in a sense that it serves a mathematical preliminary to our quantum mechanics. Okay, and also I'll repeat almost the similar thing, or probably a little less time in electromagnetic theory also. Okay, so what is how to go about it? So Dirac delta function is one, you can say that it is a generalized function. Now, what is a generalized function? I'll come to that later, but just understand it is a generalized function. For right now, just remember this term. This is a generalized function. We'll come over it in a later bit of time, but overall, understand that this is generalized function, or it is a distribution. Or it is a distribution. So both of things will come later. These are more so mathematical terms, but what you have to understand is it is defined by properties by the property that if I say that my function is a Dirac delta function, then it has to be infinite at a certain point, and it has to be non-zero for all those, accepting all those points. So for example, if I'm writing argument as x here, I will write infinite here, that is at x equal to 0, I have an infinite distribution. That is whatever is the quantity, physical relevant quantity, I don't know right now exactly, like I said earlier, that if I have to define the volume charge density of a charge, then this particular Dirac delta function will serve that purpose, because volume charge density of a charge can be written by the help of the Dirac delta function. Okay, so different other things will come along. Like what I want to say is that physical application we'll see later on, but right now just think of it as a mathematical object. So there is a mathematical object which says that you have entire distribution, or you can say you have entire contribution of that particular function along a point, at a point. So at a point you have an infinite contribution, and beyond that point you do not have any contribution. Such kind of distribution, or you can say such kind of generalized function, or what is generalized function, we'll come to that later, but such kind of function is called as a Dirac delta function. It is not a well-defined function. Understand my point? This is not that well-defined function like logarithmic function or sine function. I'm saying it is a generalized function, or it is a distribution which suggests us that the entire contribution of that particular function, or you can say that entire contribution of that particular physical quantity is at exact one point. So for example, if I have to say my charge is located at x equal to x naught, and this is a point charge, I would prefer saying that it is this way. Because as x equals to x naught, your entire contribution q is there, and if x is not equal to x naught, then it is entirely zero. You would be saying that at x equal to x naught, it is an infinite case. So I'm not saying this is charge. This is the volume charge density of a point charge, which suggests that entire distribution of charge is at a point. Entire distribution of a charge is at a point, and beyond that there is no such contribution. Now we'll come to all these things also, but understand Dirac delta function is some you can relate it to whenever you are confronted upon a problem. Initially I'm saying whenever you are confronted upon a problem how to define the volume of a point charge, how to define the volume of a point mass, you can simply think over it to be represented in some sort of form of Dirac delta function. So what is a Dirac delta function? I'm reiterating. Dirac delta function is defined by a property that Dirac of x is equal to infinite x equal to 0, and at x not equal to 0, it is equal to 0. Okay. Further, this particular thing is, another property is that this particular spike, as you can see, covers certain area. and that area is normalized to unity. That is, the first thing is this. The second thing is, if you try to integrate whatever this area holds. So for example, if I'm saying from minus infinite to infinite, all this contribution is zero, all this contribution is zero, and exactly at this contribution, your Dirac will give some kind of area. I'm saying that area under this spike should be equals to 1. So this is how you define a Dirac delta function. So Dirac delta function is a function, or you can say it's a distribution, or you can say it is a generalized function. On generalized function, I'll come later, but it is a distribution which suggests that the entire contribution to which your Dirac delta function is relevant is at a point. The entire distribution of that particular physical quantity, or you can say that particular, so you can say that it is infinite at a point, and for all those points except that particular point, your contribution is zero. Further, if you see that this is a spike and this area under the spike should come as 1. So in order to define a more proper sense, I would say that area under this spike should be normalized to unity. Okay. Now, another thing is that, for example, if this spike is not at x equal to 0, how can you redefine the function? So I can redefine the function by saying that if at all my spike is at x equal to a, then I would write Dirac of x minus a is equals to delta if x is equal to a, and it is equal to 0 if x is not equal to. Okay. Now there's a problem with all these kinds of functions, where there are delta function. How to realize them? I mean, how to realize them in some sort of way that we know already. So, for example, if I say that if I want to express this function, how to express this function? How to express this function in more appropriate manner, which I know already. Okay. So let us see that also. Okay. So let us see that. So one such function you already know. So one such function you already know, that can be one such function can already be there that you can know is a Kronecker delta function. Okay. So what does Kronecker delta do? Kronecker delta works as if it is a filter. So for example, if I'm say Kronecker delta, then delta ij is equal to 0 if I is not equal to j, and if I is equal to j, then it is equals to 1. Okay. So this is a Kronecker delta function. So for example, if I am provided by a sequence a1, a2, a3, dash, 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 an plus 1, and dash, 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 and let's say you have this, like you can say ai plus 1, and you say n. And let's say this is your sequence. If I say I have to extract 1 out of it, let's say if I want to say what will be a2, how to extract it? How to extract this particular function? How to extract this particular function? So what I would do, I would simply multiply my AIs, or you can say if I want to extract AI, let's say, so it remains a general case. So if I want to extract my AI, what would I do? I would simply multiply my Kronecker delta with it. Now, if I is equal to j, then it is equals to, if j is equal to I, then this will be equals to 1. Otherwise, it will be 0. So if j is equal to I, then it will give you AI in return. So I can write, or even if I sum it all over for entire j. So let's say if my j is equal to 1, I is not equal to 1. So if j is equal to 1, then Dirac of Kronecker delta I 1. Here you will see that there's a 1. And since I is not equal to 1, so therefore this will be 0. So overall term will come 0. And in short, it will return you something called as AI. So you can say that it filters out a point in the sequence. So what does Kronecker delta do? Kronecker delta filters out a desired point from the sequence. Okay. Similarly, if you see how would Dirac delta function behave? So for example, if I'm saying my function, Dirac delta function, is at x equal to x naught. So what does that mean? That means that at x equal to x naught, I have a certain infinite contribution. Otherwise, I do not have any sort of contribution. So that is, at x not equal to x naught, I have 0. At x not equal to x naught, I have 0. At x equal to x naught, I have an infinite contribution, this infinite spike, with the condition that minus infinite to infinite, Dirac of x minus x naught dx is equals to 1. Okay, so this is the property of the function. Now, if I say, what if I multiply this particular function with the function fx, which is continuous Riemann integrable from minus infinite to infinite? Okay, so as you can see that if x is not equal to x naught, then this particular function will be 0. And exactly at x equal to x naught, it will give you 1. So exactly at x equal to x naught, if you just integrate it, so this is kind of similar structure you can see in Kronecker delta. So in Kronecker delta, if I had to filter out a point, if I have to filter out a point of the sequence, what did I do? I simply multiply Kronecker delta with it. I took a summation. Now, instead of summation, in Dirac delta function, what I have done, I've simply taken an integral. So if I take an integral from minus infinite to infinite, fx into Dirac of x minus x naught dx, it will give me fx naught. This is called as your filtering property of Dirac delta function. And this is an important property. You'll find quite many times I would use it. Okay. Okay. So this suggests that if I have to write the value of a function at a point, I simply multiply Dirac delta station that at that point with that particular function and integrate it all over. So what I'll get fx naught. Okay, this is very simple to see that if x is not equal to x naught, then it will be 0. Exactly at x equal to x naught, this particular function would be extracted and can be said as x naught. Because see, at x equal to x naught, you can see that your entire spike is there at x equal to x naught, whose area is equals to 1. Whose area is equal to 1. And at x equal to x naught, your function fx becomes fx naught. So eventually you just get rid of this and you get this kind of thing. This you can see there is a quite striking similarity between the Kronecker delta and the this Dirac delta function. So you can say that this is a kind of discretized version, and you can see this here is there's something sort of continuous kind of thing. Okay, so here is a discretized case, and here it is a continuous case. I hope it is clear. Now, let us move ahead and see whether it is possible to somehow visualize Dirac delta function. So can we really visualize it? So let us see how can we visualize it. Okay, for that, I would say, can we visualize? Here I will write, can we visualize in terms of function that we know, in terms of functions, or you can say in terms of conventional functions that we know, like exponential or something of that sort? The answer to this problem would be yes. Let's see how. So you can take some sequence of family of functions. You can take sequence of some, you can say sequence of some functions, or you can say some family of functions. Family of functions that almost behaves as if it is a Dirac delta function. So if you have to think over some sequence of function which actually behaves as if it is a Dirac delta function, that is, you can say that if I'm saying about a function at x equal to x naught or x equal to 0, in general, let us write x equal to x naught, then what are the desired property? Property number 1 would be it should have a peaking behavior at x equal to x naught. There should be some peak at x equal to x naught. In fact, you should also be able to see that if I say that here it was a narrower case, but let's say if I broaden it somehow, although it is not the case, you understand my point. Dirac delta function is exactly having an infinite contribution at x equal to x naught. So it's actually a spike. It's not even a width here. But let's say if I have to approximate it to some sequence of function, then let's say if I have certain function which behaves like this, and it gets narrowed down as I take a limiting behavior, it gets narrowed down, so it will become a spike. So if it is the case, then it should be symmetric also. So understand my point. It should be symmetric about x equal to x naught. And incidentally, you should understand that Dirac delta function is also a symmetric function. Whether you write this or whether you write this, it is one and the same thing, because after it will become 0 at x equal to x naught only. Whether you write x minus x naught or you write x naught minus x, they are one and the same thing. So you can also write here that Dirac delta function is a symmetric function. Overall, we're trying to find that if at all, can a Dirac delta function be represented as a sequence of some function or family of some function. So in order to be defined, in order to define a Dirac delta function as a sequence of some function, you need some certain behavior. The behavior should be that it should have a peaking behavior, or it should have a peak at x equal to x naught. It should be symmetric at x equal to x naught. And also that it should be integrable in a manner that integral infinite minus infinite to infinite dx over that particular function. Let's say if I'm saying, let's say this is phi of x, it should be equals to 1. Okay, is that clear? Okay, so is that clear? So now let us move ahead and let's see how to define certain functions of the in this manner. So I'll go one by one, and we'll see how to. So sorry. Let us first take an easy example. Let us take first easy example, which is certainly you can take them as a sequence of some rectangles. Sort of rectangles, not exactly rectangles, but let's see. What I can do is, can I not write my function in this manner? Dirac nx, okay, it is equals to what? It is equals to 0 if x is less than minus 1 upon 2n. Let's say if x is lying between minus 1 upon 2n to 1 upon 2n, then it has certain contribution defined by n. And if x is greater than 1 upon 2n, then it is again 0. So if my sequence of function, I'm not saying Dirac, sorry, you can just take it as some function del and x, which is equals to 0 if x is less than minus 1 upon 2n. And if x lies between minus 1 upon 2n to 2n, then it is equal to n. And if x is greater than 1 upon 2n, then it is equal to 0. So let us try to make a plot of it. Let us try to make a plot of it. Okay, what does it say? It says that you take 1 upon 2n here, let's say. If you are keeping n equal to 1, then this will be half. And you are saying that your function only exists at this particular point. And except that these two, if I'm not talking about between points minus 1 upon 2n to 1 upon 2n, then this will be 0. This will be 0 here, and this will be 0 here. Is that clear? Now see, if I keep on increasing my n, that is, if n tends to infinity, I'm moving closer to 0, isn't it? So if I'm saying n tends to infinity, then I'm moving closer to 0. That is, if I'm moving as n tends to infinity, then this particular 1 upon 2n will start shifting towards 0, isn't it? So, and also that I can say that if it is 1, then 1 upon 2, it is 2, 1 upon 4, 1 upon 5, 1 upon 6, 1 upon 8, so on and so forth. And you'll find that it is somewhere, as n tends to infinity, it is closer to 0. Okay, this is one thing that you can realize. That as n tends to infinity, 1 upon 2n will start moving towards 0. And also that you can see that this will not come down, Rather, it will start, sorry, this will start moving up. Because you see, between minus 1 upon 2 and 2 plus 1 upon 2n, your function behaves as if it is n. And what is n? As n tends to infinity, your this particular definition will blow up. It will start blowing up. And also understand that as n tends to infinite, x is tending towards 0. So as x tends to 0, this particular quantity will keep on rising, keep on rising, keep on rising. So eventually you will come closer to 0, and you're getting, the functional value is getting closer to infinite. Is that clear? So these sequence of function would eventually look like a Dirac Delta function. So these sequence of function would eventually look like a Dirac Delta function. So I can say if I keep on increasing my n, let's say if I'm saying my n is 1, then I am having 1 upon 2n, 1 upon 2n. This will be equals to what? 1. Okay, so this is like this. So if I'm saying that my function, my n is 1, then minus 1 by 2 to 1 by 2, your value of the function should be 1. If I'm saying n equals to 2, if I say n equals to 2, then I'm in minus 1 by 4 to plus 1 by 4, my function value will become 2. And so on and so forth. If I keep on increasing these values, this will keep on increasing. And in the limiting case, as n tends to infinite, this will become like this. So you're having a narrower spike at x equal to 0, you can say, as n tends to infinite. What sort of function does this look like? This look like a Dirac Delta function. So this is an adequate representation, or this is an appropriate representation of this sequence of function as n tends to infinity would eventually define me a Dirac Delta function. Okay, so I can write that my Dirac Delta function can be represented as the limit of this sequence of function. And why I'm doing this? Why I'm doing this, you can clearly see that my Dirac Delta function as such, in the sense of conventional function, there is no such function called as Dirac Delta, because you see, I cannot say that my function is exact infinity at a point, and for all these points, it is 0. So I can only, in my functional, in the functions that I know till now, I can only see some tendency. At x equal to 0, at x tends to 0, I can say that function. But here I'm saying I need a function which behaves this way. Like it is equals to infinity at x equal to 0, and otherwise it is not. It is nowhere. It is nowhere to be seen. It is actually 0. So no such function exists. In the theory of functions, we know till now. Obviously, this requires you to go into some very rigorous theory of generalized function, which I'm not right now interested in getting into. But overall, just try to develop a flavor that in order to define Dirac Delta function, we actually sometimes resort to functions of a sequence of function. A limit of sequence of such functions almost resembles the definition of the Dirac Delta function. One such function can be this, what I have written, that it can be 0 if x is less than minus 1 upon 2n, and if x is greater than 1 upon 2n, then it is equal to 0. So what does it suggest? It suggests that if you go as n tends to infinity, you are on the right hand side of 0. On the right hand side of 0, you have 0. And if x tends to infinite, this is less than 0 from the negative side. So you can say it from negative side approaching 0, it is again 0. And almost close to 0, that is if x tends to n tends to infinity, then actually I'm talking of 0 only, because here the limit will be 0, here the limit would be 0. So I'm saying at x equal to 0, my limit is infinite. So this particular function, when I will take the limit of this sequence of function, it will almost behave as if it is a Dirac Delta function. Okay, let us see a few more sequence, and we'll end this lecture here only, and we'll go along doing some more properties about Dirac Delta function in the next lecture. So can we not represent our function in this manner? Dirac n x is equals to n upon root over pi e की power minus n square x square. Okay. Now clearly see, as n equals to 0, as x equal to 0, this will be equals to 1. And if n tends to infinity, this will go towards infinity. And if x is not equal to 0, and if n tends to infinity, you can clearly see that this is n. And if x is non-zero, and n tends to infinity, this is like this kind of thing. So I want to say that if x is non-zero, so this will remain here. And as n tends to infinite, you can clearly see that your exponential will rise very quickly than n. You can see this is the function of exponential. And this is how your function x behaves. So if I'm saying n here, and if I'm saying, let's say x is non-zero, then just take it as like whatever constant value you want to take it. But overall, understand this behavior would in any case be very dominating over n. As n tends to infinity, your e to the power n square would rise up as fast as possible as compared to n. Overall, this term will go to 0. Okay. And also look at this particular function. This is quite a function that you already know. This kind of function you quite many times draw in your classes. So this looks sort of Gaussian. So you can say that this is a symmetric function also. So you can see that Dirac minus and Dirac, you should not say Dirac here. So this kind of function, if I replace x by minus x, this is completely symmetric. This is a symmetric function. Also, it shows a peaking behavior at x equal to 0. How do you see that? So let me write x equal to 0. And if I take a limit of this particular del n x, what would I get? I would get, it is nothing but limit n tends to infinity of n upon root over pi, because this is e raised to power 0, e raised to power 0 is 1. So this will be equals to infinity. And if x is not equal to 0, then clearly this term would survive. And if this term survives, as n tends to infinity, compared to n, your e to the power n square will rise very quickly and very fastly and very rapidly towards infinity. It will be dominating to over n, and overall this particular term will go towards 0. So this suggests that if x is not equal to 0, my function is 0. And if x equal to 0, then my function goes towards infinity. What sort of function is this? This particular function is nothing, but this is Dirac Delta function. So Dirac Delta function can be represented as a sequence of these functions also, limit of sequence of this function also. So I can write Dirac Delta function can be represented as a sequence of the above function. As the limit of the sequence of functions as given above. Okay, so I would say that my Dirac Delta function can be written as, like till now, what I have written. For example, if I write limit n tends to infinity, my del n x can be written as Dirac x. If your del n x is equals to n upon root over pi e raised to power minus n square x square. Also, you can write del n x as some rectangles that I told you in the very start of the lecture. Okay, so further as I move along, I'll start putting some more examples as I go along. One such function can be, you can say, like family of Lorentzians also. So one such function can be family of Lorentzians. So you had a family of rectangles, you had family of Gaussians, you can have family of Lorentzians as well. Okay, so the function like this okay, functions like this. Now clearly see that x equal to 0, at x equal to 0, this will be 1, and as n tends to infinite, your del n x goes towards infinite. So at x equal to 0, this is 0, 1 plus 0 is 1, and as n tends to infinite, this will become infinite. Also, if x is not equal to 0, then obviously this is n squared. So obviously the term which is in denominator is more dominant over the term which is in numerator. And as n tends to infinite, you can clearly see that your n square will go very rapid than n. So obviously this entire term would go towards infinity, and overall this term will go towards 0. So I can as well as say that if I am representing my Dirac delta function as a limit of family of Lorentzian, then also it will be the right thing to say, because limit n tends to infinity for this sequence of function would look like as if it is a Dirac delta function. Okay, so this definition, at times you see certain modification. Instead of n tends to infinity, you will find epsilon written there and epsilon tending to 0. Because you see, if I take epsilon tending to 0, instead of n, I can write 1 upon epsilon in the structure, and I can replace the same thing. Okay, so I can replace the same thing. Okay, so I hope this is clear to you. A few examples in terms of epsilon if I want to write things up. Okay, another thing that you can do is, okay. Okay, so another thing that you can do is, in terms of epsilon, if I try to write, so for example, let us see, can these functions uh, tend to a Dirac delta function as epsilon tends to 0. So as epsilon tends to 0, does any of these functions which I'm going to write, are they going to look as if this is a Dirac delta function? Let us see. So for example, I start with a function like this. Okay, this is the function. Now clearly see that if your x is equal to 0, then this will be 1. And let's say epsilon tends to 0. If epsilon tends to 0, this will tend to towards infinity. So this particular function, if I say, let's say represent it in this fashion, as epsilon tends to 0, if x is 0, this will become 1. And epsilon tending to 0, this will become infinity. And if your x is non-zero, and your epsilon tends to 0. If your x is non-zero, clearly see if your x is non-zero, then this entire term would lie below. Like I would write in this fashion so that it becomes quite understandable to you. See, now understand my point that as epsilon tends to 0, this will tend to 0 and this will also tend to 0. But in any case, you have to remember one thing, that the diminishing behavior of e raised to power something is way greater than blowing like blowing part of this particular function. So how would you do that? Just try to differentiate it, or you can see if epsilon is tending to 0, overall understand, and if x is not equal to 0, then this particular term is rapidly going towards 0, rapidly approaches 0. See, for example, I'm saying e की power minus x, इसका behavior कैसा होता है? It is like this. Now, if I'm saying I'm multiplying this particular thing with a scalar, and this scalar is rapidly moving towards infinity, So how would you how can you say, can we not say that this particular function would tend towards 0 before this particular function tends towards infinite? Because here is a confusion. Anybody would say that this epsilon is tending to 0, so this is becoming some infinite kind of thing, and as epsilon tends to 0, this is becoming some 0 kind of thing. So which function will dominate? Obviously this particular function will dominate, because even if it's a large quantity, this is very diminishingly small. You can take it in a manner that if I say my epsilon tends to 0, and let's say if my epsilon is, let's say 10 to the power minus 12. So this particular factor which I'm writing would become around, in order, it will become around 10 to the power 12. But overall, understand this particular function, if when multiplied, will become e raised to power minus mod x. And if I divide by 10 to the power 12, so it will be into 10 to the power 12. So understand my point. Exponential raising to the power 10 to the power 12 and 1 over it. So this particular term will move towards 0 as fast as possible. And overall, this particular term will go towards 0. This is something that you should be realizing. So you can see that if x is not equal to 0 and the limit epsilon tends to 0, if x is not equal to 0 and limit epsilon tends to 0, this entire term would move towards infinity raised minus, and this entire term would move towards 0 overall, because this is infinite. Here it is a negative sign. So overall, this will become 0. But if your x is equal to 0, then this will become 1. Even if epsilon tends to 0, however epsilon small might be, overall it is not a 0. So this is not a 0 by 0 operation. You can say that epsilon tends to 0 means epsilon is coming close to 0, overall not equal to 0. And x equal to 0, this will become 1. And understand my point, this will become 1, but this quantity still remains. As epsilon tends to 0, this overall term will go towards infinity. So overall, understand that this particular function in the limit epsilon tends to 0 indeed would behave as if it is a Dirac Delta function. I think it is clear. Another good part, if I say this kind of function, so I have already done the function of this sort, but I'm just repeating it for you so that you should be able to get it. For example, if I write this way, now you can see that if x is equal to 0, then this particular part will become 1. This particular part will become 1. And as epsilon tends to 0, overall this particular function will go towards infinity. So if I write it as again some phi epsilon x, so this phi epsilon x goes towards infinity. I hope it is clear. Now, if I just try to see that if x is not equal to 0, then how would the function behave? So if x is not equal to 0, so if I write x is not equal to 0, then what will happen? If x is not equal to 0 and as epsilon tends to 0, if x is not equal to 0, so this entire term you can see will exist. Okay, and it will become infinitely large, because you see x is not equal to 0, this will be some positive quantity, and divided by some tending to 0, overall it will become some infinitely large quantity, and e raised to power minus infinitely very large quantity would become 0, and it will be dominating over this particular term. Understand my point? So this will become 0 if x is not equal to 0 and epsilon tends to 0. So this particular function in the limiting case epsilon tends to 0 would behave as if it is a Dirac Delta function. I hope it is clear. So this brings me to a closure of this lecture, but I want to leave this particular lecture with a problem that I'll give you. Just have to see and tell me whether this function that I'm writing right now this particular function, does that behave in the limiting case epsilon tends to 0 as a Dirac Delta function or not? And this will serve as a major motivation as we go along. So you have to tell me whether this particular function as epsilon tends to 0 behaves in a manner of Dirac Delta function. Or in other words, can I write this particular limiting behavior as Dirac Delta function? I hope all these things are clear. So in short, you should remember that there are physical situations there where we may be requiring a function which is only defined at a point, and that definition is infinitely large, and otherwise it is 0. Like example of point charge and point mass I gave you. These are just examples. This is not it. This is not all, but I'm just saying this is an example. That if I want to define a volume charge density of a point charge, how would I do it? Because in order to define a volume, you need some dimension, like you need some dimension, but point has no dimension. So if point has no dimension, then obviously this particular point charge should be represented as having an infinite contribution at the point, and for all those points where it is not there, it should be 0. So such distribution or generalized sort of explaining things can be well encapsulated in a mathematical construction. I'm saying not function exactly, in a form called as Dirac Delta function, which suggests that x equal to 0, it is equal to infinite, and x equal to not equal to 0, then it is equal to 0. So just focus on this argument. If this argument becomes x minus a, then at x equal to a, that is when x equal to 0 here, x equal to a, that should be infinite, and x not equal to a, that should be 0. Then I also told you that it is constructed in a manner that this area under spike should be normalized to unity. So minus infinity to infinite Dirac dx should be equal to 1. And further, as we move along to a discretized, you can say analog to it, how would I say? I would say that there is a function called as Kronecker delta, which suggests del ij is equal to 0 if I is not equal to j, and if I is equal to j, then it is equal to 1. So if I say, let's say point a1, if I let's say sequence of points a1, a2, a3, ai plus 1, an is there, and if I want to filter out this ai, what I would do, I would simply multiply ai with Dirac ij. And if I multiply it with del ij, sorry, again Dirac, I've told you, del ij or Kronecker delta ij, this Kronecker delta ij would become 1 only if I equal to j. So if j is equal to I, only then it will become 1. Otherwise, it is 0. So if I sum it all over, let's say ai into Kronecker delta ij, if I sum it all over, then if j is equal to 1, this will be 0. If j is equal to 2, this will be 0. If j is equal to 3, this will be 0. If j is equal to I, this will be 1. So overall, you can just filter out one point of the sequence, that is ai. In a similar manner, if I just convert this particular thing into a continuous sort of way, I'm not saying this is an entire mathematical derivation, but I'm just trying to make a motivation in order for you to understand that for a continuous case, I can write the same thing from minus infinite to infinite. Instead of Kronecker delta, I'm using a Dirac delta function. So this Dirac delta function is 0 if x is not equal to x naught, and it is equal to some infinitely large quantity whose area under would come as 1. So at x equal to x naught, this will become fx naught. Overall, this area would become 1. So your function would filter out like fx naught. Now, another thing is, in terms of conventional functions, can we really visualize your Dirac delta function? The answer to this question is yes. We can see some. We saw some family of functions. We saw some family of you can say some sequence of some functions whose limiting behavior supposedly represents your Dirac delta function. And the question is, the requirement is that function should be symmetric. The integral of that particular function over the entire range should come as 1, and the peak should be there at some point. So let's say if I have to define my Dirac delta function at x equal to x naught, then I should have a peak at x equal to x naught. It should be symmetric at x equal to x naught. And further, this particular function whose limiting behavior is like Dirac delta function should be integrable, and this integral should come as 1. So one of the examples that I taught you was sequence of rectangles. You can see that as x tends to n tends to infinity, this will go towards 0 from the left hand. This will go towards 0 from the right hand. Overall, sorry for the interruption. So overall, it will behave okay, sorry. So overall, these sequence of rectangles would behave as if overall these sequence of rectangles as n tends to infinity would behave as if it is a Dirac delta function. Similarly, I taught you these sort of Gaussians. You can see that if x equal to 0, then this will become 1. And now as n tends to infinity, this will become infinite. And if x is non-zero, then this particular term will become 1 upon e to power n square x square. And as n tends to infinity, this entire term would go towards 0. You can see in this manner also, like if you're getting confused, then just do one thing. You just write n upon root over pi e raised to power minus n square x square. If x is not equal to 0, then this will be some positive term. Forget about it. So you write e to power minus alpha n square, and you can write this, and there is n, and 1 upon root over pi. I'm now saying find the limit n tends to infinite. Now try to find n tends to infinite. So n tends to infinite. This is infinite. This is infinite. Try to write L'Hopital rule. This is 1. This is alpha e to power alpha n square, and then you have some 2 alpha. In any case, you can see that this entire term will become very large, tending towards infinity. Overall, this entire term will tend towards 0. So overall, try to understand my point that as x is not equal to 0, as n tends to infinite, this particular sequence of Gaussians would correspond towards 0, would move towards 0. And if I'm saying if x is equal to 0, this is becoming 1. As n tends to infinity, this will go towards infinity. So this is a kind of definition that you see in the Dirac delta function. That is, at x equal to 0, the function is tending towards infinity. In fact, here at x equal to 0, it is infinite, and x not equal to 0, this is 0. So you can see that these family of Gaussians in the limiting case can resemble your Dirac delta function. Okay. Similarly, as we went along and we saw that family of Lorentzians represented by n upon pi, 1 upon n square pi square, n square x square. This also represents in the limiting case your Dirac delta function. So if I write x is equal to 0, then this is some 1, and n tends to infinite, this will becomes infinite. So as x equal to 0 and n tends to infinite, this entire thing would become infinite. It's infinitely large, you can say. So, and at x not equal to 0, this will be something here, n upon something 1 plus n square. So obviously this entire thing as n tends to infinite will be very, very, very large. And when it is very large, this will overall, this particular term will become 0. Are you getting my point? Just try to again concentrate. If x is not equal to 0, this will remain something here. N upon 1 plus n square something. So n square obviously is greater than n. As n tends to infinity, your denominator is dominating over your numerator, and this will become infinitely large, and 1 upon infinity large will go towards 0. So if x is not equal to 0, your function is going towards 0, and if your x is equal to 0, then your function is going towards infinite. So if x is equal to 0, your function is going towards infinite. If x is not equal to 0, your function is going towards 0. Overall, this is the description of a Dirac delta function. Further, I just changed my definition. In certain books, you'll find these definitions. Instead of writing n tends to infinite, they would write epsilon tends to 0. This is one and the same thing. And I taught you the two ways of doing the same. So for example, if I just try to plot a graph of e raised to power minus x, minus modulus of x. So you'll find, okay, let us come to this particular function just to pictorially represent, because I forgot to do so. So if I say, what is e की power minus modulus of x? How to make a graph over it? So if you just see, this is your e की power x I'm making, and this is your e raised to power minus x. So this is your e raised to power minus x. This is your e raised to power x. How would things behave? So I'm saying modulus of x. What does modulus of x means? Modulus of x is equal to x if x is greater than 0, and it is equal to minus f x if x is less than 0. So if I'm saying x less than 0, I have to make a plot of e की power minus of minus x, that is e की power x. So for all x less than 0, I'll make a graph of e की power x. And for all x greater than 0, I will make a graph of e की power minus x. So this will be some this kind of function. And this is clearly non-differentiable because here it is a sharp peak. And if I try to multiply it, you see, if I try to, this will be of this way. Okay. Now, instead of this, I will write e की power minus mod x upon epsilon. Okay. Now, as epsilon tends to 0, this particular argument will become infinitely large if x is not equal to 0. Obviously, if x is, okay. So if you see that if x is equal to, if x equal to 0, I think there should be some epsilon also. No? Okay, some epsilon also is multiplied. Okay. So if I multiply an epsilon with it, I think I have multiplied with some epsilon, or did I not? Okay. So I've multiplied it 1 upon 2 epsilon. Sorry. So I've multiplied with a quantity 1 upon 2 epsilon. So multiply it, just remember this term. So if I try to multiply with 1 upon 2 epsilon, now see if x is equal to 0, if x equal to 0, this is 1. If x equal to 0, this is 1. And here is a quantity which is associated 1 upon 2 epsilon. Now, as epsilon tends to 0, this is 1. This will go towards infinity. Now, if x is not equal to 0, and epsilon tends to 0, it implies modulus of x upon epsilon would go towards infinity. So you can see that this is going towards infinity. This is going towards infinity. And as this is going towards infinity, you can say e raised to power minus infinity or e raised to power minus something which is very large, it goes towards 0. So this entire thing is going towards 0. And this cannot stop it. You will say that as epsilon tends to 0, this should go towards infinity also. But understand my point, this 1 upon 2 epsilon, as it grows, it cannot grow as rapidly it is going towards 0. You can see that the growth of this particular function, or you can say the decline of this particular function is too very rapid than the growth of this particular function, that I'm leaving for you to see. You can just take a derivative and you can just apply L'Hospital rule, and you can do that also. But in a manner I'm explaining, this is a kind of physics perspective I'm giving to you. For example, the decline that this particular function would have as epsilon tends to 0 would be way too much than the rapidity, or you can say the growth of this particular function. So overall, this multiplication would go towards 0. Otherwise, it's very simple to see. If you just represent it as 1 upon e की power mod x upon epsilon, take a L'Hospital rule, you are able to do that also. So overall, as epsilon tends to 0, this particular function, which is 1 upon 2 epsilon, e raised to power minus mod x upon epsilon, would behave in a manner your function Dirac delta behaves. I hope it is clear. So I'm leaving you here with a question, which is this. And this will serve as a major motivation in your further lectures. And you'll see how. So this is your homework. Try to do this particular problem as a homework, and we'll meet tomorrow. Till then, take care.